This is a total production. Alright, Chem Minions, this is going to be our second practice video for Chapter 2. Here we're going to look at drawing resonance structures. And so with that, some things we want to remember, right? Resonance structures really occur when we have a few scenarios. For instance, we're going to need to see something like a double bond and a single bond. And then at the end of this single bond, right, this carbon here, or this atom, whatever it is going to need some type of charge, whether it's a plus charge, a minus charge, or even just a lone pair. So you could have something like an oxygen with two lone pairs here, right? So that could have resonance, or you could even have something where you have a plus charge or a negative charge. Anytime you see this type of motif, right, motif. That's a fun word to say. But anytime you see this type of motif, you're going to have the option of electrons being able to move around. And the whole point is we move from electron rich towards electron poor. And so in terms of being electron rich, we're looking at anything that's electron rich tends to be something where we have pi bonds, right? So double or triple bonds. And if we have lone pairs, right, or even if you have a negative charge, right, that's usually a good indication that whatever has that negative charge is in fact electron rich. So if we go and we look at this structure right here, we can see this double bond, single bond, and then the carbon here has a positive charge. So as we look at that, this double bond is gonna serve as our electron rich area, while this positive carbon is definitely going to be electron poor, right? If it were electron rich, it would either have pi electrons, lone pair electrons, or even a negative charge. But a positive charge is a lack of electron richness, all right? So what we're going to do is we're going to see that our electron rich is going to move in the direction of our electron poor. Now, you'll notice here I'm drawing this arrow, and this arrow is showing that two of the electrons from the pi bond are shifting to right here between these two carbons, right? It didn't go directly to that carbon, right? Because you can't completely rip those pi electrons away from both carbons. Those pi electrons have to stay with at least one of its original carbons, right? So it's going to shift to right here. So now it's being shared there. So that means when we go and draw this backbone, let's say 1, 2, 3, 4, 5, 2, 3, 4, 5, and then we're going to have a carbon coming off there. So now the double bond is going to be between these two carbons right here, which would put it there. Now, this moved in this direction so that we could get rid of the positive charge on the carbon. But the problem is we didn't bring in extra electrons, so that positive charge has to be floating around somewhere. Well, it makes sense that this carbon, right, that one there, no longer has its original pi bond. So it's the one that is now electron poor. And so this is pretty much our only resonance structure for this. Right, we can't move our pi bond anywhere else. Right, we can't move it up here because that carbon doesn't have a charge on it. So that tells us it already has 4 bonds, which means it has an octet. Right, there are 2 electrons in a bond. The pi bond can't move to this carbon because this carbon has 2 shown, but there are 2 hydrogens there as well. We know that because that carbon doesn't have a charge. So there's really nowhere else for this pi bond to move. All right, and so I guess I'll show the 3 hydrogens as well. Hydrogen, hydrogen, hydrogen. So, all right, so looking at the second one here, showing all the possible resonance structures, we see double bond, single bond, and a charge, right? That's exactly what we saw up here. So we can see this double bond can shift to now up here between these 2 carbons, right? So remember, I can't rip those pi electrons away from both of the carbons, right? It's got to stay with one of the 2. So what we would see here, I didn't touch that pi bond, so I'm going to leave it. Okay, and then this pi bond shifted up here to right there. Okay, now in terms of what has now happened, this carbon is no longer positive because it got the pi bonds. But this carbon lost its pi bond, so now it has the positive charge. Okay. Now if you notice, there is one additional resonance structure I can draw for this because I have a pi bond and I have a single bond, and then that carbon has a positive charge. So I can see this pi bond shifting to right there now to give me All right, there's the backbone. So I didn't touch that pi bond, so I'm going to leave it there. And then now the pi bond shifted to over here, right there. And this carbon lost its pi bond, so now that's why I'm going to put the positive charge there. Okay, so the big takeaway here is always conserve your charge. If there was a positive charge on something, odds are the positive charge is going to be in the new resonance structure you draw as well. All right, or the way you can think about it is, and this is going to be accurate most of the time, more often than just saying put the positive on something else. If you notice, this entire structure had an overall positive 1 charge. So this structure has to have an overall positive 1 charge. And the same with this one. Okay. Now, if we look at this third option here, this guy now is very similar in structure, but instead of a positive charge, it now has a negative charge. And what that tells me, if you recall back from formal charge, this carbon has 1 hydrogen, and it also has a lone pair. That negative charge comes because of the existence of that lone pair. And so you've been seeing pi bond moving towards positive, but now we don't have a positive charge. We have a negative charge. Negative means that's probably the most likely electron-rich area. And so in this case, when the electrons move, those lone pair are going to move to right here, right? So it's still going to be associated with the original carbon, but it's now going to form a pi bond. And then what does that do? See, this carbon right here has a hydrogen, so that carbon already has 4 bonds. So this pi bond has to move out onto the corner carbon here. So we're looking at a resonance structure where the pi bond is now up here, and I didn't touch that pi bond, so I'm going to put that one back there. All right, and remember, this corner carbon now has the pi bond moving out as a lone pair, like so. And what does that mean? Now that that carbon has a lone pair, it's going to have a negative charge as well. Okay. Now you notice, just like before with this guy having this additional pi bond, right? This pi bond can now move. So we've got that lone pair. You notice I'm repeating the exact same thing I did in this first step. The lone pair is going to move here, form a pi bond. That will then force this pi bond out and push it onto this corner carbon right there. So let's look at that. We got boom, boom. So those would be where the pi bonds go. And now this carbon has the lone pair, aka the negative charge. All right, and then at this point I'm done. I can't make any new resonance structures. And so big thing to also remember here is I can't move this lone pair this way, right? Because this carbon, even though there's only 3 bonds shown, there was never a charge on it. So that tells me there's this invisible hydrogen there. And so I can't exceed my octet. I can't exceed 4 bonds on those carbons. All right. Looking at this guy here, what I have, I don't see a charge anywhere, but what I do have is a double, single, double bond. And the other thing is I have an electronegative oxygen. This oxygen really wants to pull those pi bonds up to it because it's so electronegative. And this is feasible to happen in that I could form this structure here, right, where now I'm going to get a negative charge on the oxygen and a positive charge on the carbon. And that's kind of weird, but technically that is considered a resonance structure. But also, having now a double single bond and a charge, this pi bond can move up to there to give us, let me get it drawn up here. So we now have a double bond there, and this carbon lost the pi bond, so it gets the positive charge. And all of these are feasible because I did conserve my overall charge, right? There's a 0 overall charge, +1 -1, a 0 overall charge, +1 -1, a 0 overall charge. All right, next up we have this double bonded oxygen and then a nitrogen singly bound with a negative charge. So that actually means that this nitrogen has 2 lone pairs on it. All right, we saw that in the formal charge practice video. All right, and so what this means is the nitrogen is more or less electron rich. And so one of these lone pairs could move here between the carbon-nitrogen bond. But because of that, this pi bond has to move up to the oxygen. Very similar idea to what's happening here, right, in this first resonance structure we drew. So we're going to see, boop, 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 5-membered ring. We're going to get a double bonded carbon to a nitrogen, right, like so. And so it's going to lose its negative charge, right? And then we're going to get a single bonded oxygen. And it started with 2 lone pairs, and now it's going to have 3 because the pi bond shifted up. And so the negative charge is now going to be on the oxygen. All right, and that's it. That's all we have for the resonance structures for that. All right, just 3 more. All right, next up, we have a negative oxygen with a single bond and a double bond. Well, guess what? The electron-rich area here is going to be the oxygen because it's negatively charged. And when it has that -1 formal charge, that means it has 3 lone pairs on it. All right, also in the formal charge video. All right, we're going to see one of these lone pairs can move here between this bond right there. All right, my arrow's looking kind of funky, but there it is. All right, next up, that's going to force this pi bond to move out to this corner carbon. Why? Because that carbon already had 1, 2, 3, 4 bonds, so it can't get a 5th bond. So that pi bonds are floppy, it has to move out to the carbon. So we're going to see the lone pair now on that carbon up here. I didn't move this pi bond, so I left it. And now I'm going to get a double bonded oxygen with 2 lone pairs. And I conserve my charge, right? -1 overall, -1 overall. All right, from there, what can happen? I've got a new negative atom, and I've got a new pi bond in the mix. So this lone pair can now shift here, forming a pi bond, and then this will push the pi bond out as a lone pair on that corner. You notice I'm pretty much repeating the same move again, right? So anytime I draw an additional resonance structure, I tend to repeat the same move over and over again. So if you can at least get the first one, a lot of times you can get the rest of them after that. Alright, so I didn't touch the double bonded oxygen, but now I'm going to have a double bond here, which would go right there. This pi bond moved out as a lone pair right here to give me a negative charge there. Alright, and at this point I've pretty much moved every double bond, so I don't really have any other resonance structures I can work with. So these would be the 3 resonance structures. Next up, I have, we're back to a positive charge. Here I have a carbon. This carbon right here has a positive charge. So that means that the bonds shown on carbon are all that's there. So there's only 6 electrons around that carbon. Now, that positive carbon is bound to an oxygen with 2 lone pairs. Since there's not a charge on it, I know those 2 lone pairs are there. So what we can see happen is these electrons, lone pair, can move here and form a pi bond right there. So I would see as my resonance structure, the oxygen now has a double bond, a single bond, and only 1 lone pair. And that would force the positive charge here on the oxygen. Okay? Alright, and that's it. We don't really have anything else for that one. Next up, we have another carbon with a negative charge. And so that means that this carbon has a lone pair, but it also has a singly bound hydrogen. Okay, so it does have 8 electrons, right? 2, 4, 6, and 8, but one of those bonds is a hydrogen, so I just drew it. Now, remember, we move from electron-rich to electron-poor. So electron-rich is our negative charge, and we can really only move this direction to form a pi bond between the 2 carbons, and that's okay because we have a pi bond here that can move up onto the oxygen. So the only resonance structure we're going to have available to us is this, right, where the double bond is now here between the 2 carbons, and then that oxygen now has 3 lone pairs and a negative charge on it. So we did conserve the overall -1 charge as well. Alright, now this is not exhaustive, but resonance is very important for you to get. And I actually, in a few more chapters, I'm going to post another resonance practice because it's specific to aromatic compounds, but you really need to understand these resonance structures, right? And you want to do the simplest number, the smallest number of electron movements per resonance structure, okay? So usually, if you start doing more than 2 arrows, right? 2 arrows, 2 arrows, 2 arrows, 1 arrow, 1 arrow, 1 arrow. But if you ever are starting to do more than 2 arrows in your electron pushing, then odds are you're actually doing more than one resonance move at a time. All right. But anyway, so this concludes the resonance practice for chapter 2. Stay weird.